Okay, so chapter 2. Today we're going to be learning about atoms and the chemical nature, and really the subatomic nature of the atom, and really the periodic table. We're going to be exposed to a lot of the really important things that are in chemistry. So let's start from historical point of view. Around 384 BC, Aristotle just this is all observation. So they didn't have any technology to do experiments on an atomic level at this point. All you can do is just ponder the existence of things, just like Newton at first pondered the existence of gravity because things fell down. And then he finally invented calculus. This guy invented calculus to have calculations and mathematics behind what he observed. But a long way before that, you have Aristotle, who just thought about everything that we see in all of matter. And he says he's composed of 4 elements, like earth, wind, and fire, whatever, right? But obviously we know it's a lot more complicated than that. But that was where this idea of the atom first started out. So they came up with the term atomus, which means the point at which matter can no longer be subdivided. So that's where the word atom was derived from. But we now know that even atoms can be subdivided. We have components of the atom. We have the protons, we have neutrons, and we have electrons. So we're going to be learning about the different properties of those subatomic particles in a couple of slides. But first, there was very important laws that were developed that dictate chemical reactions and any kind of reaction change, whether it's physical or chemical change. These laws dictate it, and there's actually 3 important ones, but we're only going to go over 2 of them. The third one's kind of complicated, and it's not really important for this class. So the first one is the law of conservation of mass. So it's stating that during a chemical change, or even a physical change, honestly, matter is neither created or destroyed. So you can't react 100 grams or 50 grams of substance A and 50 grams of substance B and get 200 grams of your total product. That's not how it works. The product would be 100 grams. This is all theoretical, if you got 100% yield, meaning everything reacted completely and there was nothing that was lost into the atmosphere. But we know that in any chemical reaction, the law of conservation of mass is almost impossible to exhibit experimentally, meaning unless you have very, very sensitive instruments. So let's say we react sodium and water, right? Sodium and water, any of the group 1A metals, including sodium, they react explosively with water. So, and this is the metal itself. So a solid piece of sodium, not sodium chloride on this, obviously, because that's salt, and obviously that doesn't explode when you put water on salt. That'd be pretty cool though. But for sodium, let's say you have 2 grams of sodium and then you have 2 grams of water, and you react them together, they explode. You're not going to get 4 grams of your total because the explosion mass and energy went into the atmosphere. So it's going to be a bit less than that. But theoretically, this is true. I mean, this is true. You cannot lose mass. Mass can be converted and transformed. So mass can be transformed into energy based on E equals mc squared, but it cannot be lost. It cannot be destroyed completely or created. So law of conservation of mass, very important one. So here's an example of that. You have 100 grams of mercuric oxide, so it's mercury and oxygen put together, and then you have that decomposes into mercury and oxygen, and you see how the masses of each of their individual components, the mercury and the oxygen, add up to the total, which is 100. Does that make sense? Is there any questions on the law of conservation of mass? No? Okay. All right, moving on. So the second one is the law of definite proportions. So this one basically dictates the chemical combinatorial nature of compounds and molecules. And it's stating that a compound always contains the same elements in a definite proportion. So what that means is you have water, right? So water is a compound. It has H2O. So it has 2 hydrogens and 1 oxygen. There is no water out there that has H3O. It's a different compound. It's actually called the hydronium ion. There's no HO. That's something different. That's a different compound. It's called hydroxide. So the point is that if we're talking about water, we are only talking about H2O. That is the definition of the compound. And it, every single time, has a proportion of 2 hydrogens to 1 oxygen. So, and it's saying no matter where the source is. If you take water in the Appalachian Mountains versus New Jersey, I mean, New Jersey may be a little more dirty, but the water particles themselves will be the same. They'll be H2O. So here's an example of copper carbonate. You take it from anywhere you want, wherever all these sources are, and copper carbonate actually looks like, well, there's multiple copper carbonates. So copper carbonate could either be written, and we'll learn what this means later on in the course, but copper carbonate could be CuCO3, or it could be Cu2CO3. Those are both forms of copper carbonate. This one's called copper 2 carbonate, and this one's called copper 1 carbonate. It's sloppy, whatever. You get the point. And we'll talk about why that is probably chapter 3 or 4. And yes, I will repeat the H2O example. So it doesn't matter where you get your sources from. So if you get H2O from a river or from the ocean, the molecule itself is not changing their proportions of hydrogens to oxygens. So every single time for water, it will be 2 hydrogens to 1 oxygen, no matter where you go. Same thing for this copper carbonate. It's either, if it's copper 2 carbonate, it's CuCO3 every single time. If it's in A, if it's in B, it's in C. It's this definite proportion of copper to carbon to oxygen. For copper 1 carbonate, different compound, it's definitely the ratio of 2 coppers to 1 carbon to 3 oxygens. So it's a definite ratio that defines the compound. Okay. All right, so here's an example of that. So if we're trying to make lead sulfide, so let's look at each example at a time instead of getting overwhelmed. So if we're looking at lead sulfide, that's this black stuff over here. The reaction takes 10 grams of lead plus 1.55 grams of sulfur to make 11.55 grams of lead sulfide. This is just a definition. So you should read this. All right, fine. That's the case. You add this much lead, add this much sulfur, you get the lead sulfide. That is a ratio. That's a ratio of masses, but it's still a ratio. So you have 10 grams and 1.55 makes 11.55. Then you can see that, all right, what if we change it up a little bit? What if we had 10 grams of lead, that stays the same, and we increase the amount of sulfur? So you'll see what happens. You get the exact amount that you got before, 11.55 grams of lead sulfide, because we know the ratio of the reaction to make lead sulfide is 10 to 1.55. If you have excess, such as this 3 grams, which is excess, more than 1.55, you're going to have the remainder left over and not reacted. So that's this 1.45. That's the leftover. It's not going to react because the creation of lead sulfide is a definite proportion of lead and sulfur put together. So does that make sense? If not, ask questions.
Can you repeat that again?
Okay, so there is a definite proportion of lead and sulfur that react to make lead sulfide. And by the way, this is just an example. You don't have to memorize this reaction or anything like that at all. This is just an example of the law in practice. Now, this ratio is a definite ratio, meaning if you, in your samples, if you happen to have more of one of the components, so if you happen to have more sulfur, it's still going to react in that definite ratio. But since you have more sulfur, there'll be some in excess. There'll be some that's left over and not reacted. So the same thing applies to this third example where you have 18 grams of lead and then you have the correct 1.55 grams of sulfur. So we know the ratio is 10 grams to 1.55. So if you have 18, which is in excess, to 1.55, what's going to happen is the same thing you'll get your same lead sulfide, but you'll have lead, 8 grams of lead left over because it didn't react.
Okay, got it.
Okay, cool. Any questions there? No? Okay, good. So, law of multiple proportions. We're not really going to cover this one too much. It's the third one. But basically, so sometimes you might have elements that combine in more than one set of compounds, such as nitrogen and oxygen. There are 3 very common compounds that have nitrogen and oxygen in them, just those 2 elements. So nitrous oxide, which is N2O, nitric oxide, which is NO, and nitrogen dioxide, which is NO2. So I'm not going to test you on this one, but basically what this law is saying is that the mass of in each one of these compounds, the ratio of nitrogen to oxygen by mass is a whole number proportion to the other ratios to the other ratios mass to mass in the other compounds. So let's look at this chart. So the mass of nitrogen per 1 gram of oxygen. So you just take the mass of nitrogen divided by the mass of oxygen. You get for nitrous oxide, you get 1.75 grams. Fine. So then you do the same thing for the other 2 compounds that have nitrogen and oxygen in them. If you divide these numbers together, these ratios, you're going to get whole numbers. So why is this important? It's saying that no matter what compound you have of 2 different elements, the mass ratios are going to be similar by a proportion, by some multiplicity constant. So whether it's times 2 or times 4 or times 3 even, it's going to be the ratios of the mass. It's really weird. The ratio of the mass ratios is going to be a whole number. So yeah, that's one. Don't worry about this one. It's not going to be on tests. So I explained this one just to explain it. It will not be covered on the test. So if you want to hear it again, I'm not going to dwell on this too much because it's not too important. You could hear it on the recording. Okay. So we know this already. So all matter is composed of atoms. Atoms of a given element are very similar to each other, and this is dictated by the periodic table, which we will see in a later slide. And compounds are formed, we know this, when more than one element combines into a fixed proportion to make a specific compound. And then a good way to think about a chemical reaction is just the rearrangement of these atoms. That's all it means. So if you're reacting water with, iron, if you're doing rusting, all you're doing, I'll write that equation. I'll write the general overview of that equation. So all it is taking iron, which is Fe, plus, let's say you're reacting with oxygen. All you're doing is rearranging the atoms. It's actually going to be, we could just say it's this. So iron reacts with the air with O2, and that's called rusting, and you get iron oxide. I mean, in reality, this is not a correct equation. In reality, the iron oxide is Fe2O3, but we will go over why that is another time when we learn about balancing equations and things like that. Okay, so this is a very important slide, and I have a Jimmy Neutron meme. So wait a minute, right there, that is the atom in the Jimmy Neutron intro. So the composition of an atom, very, very important. So before we go over the definitions, I'll just explain to you the scale of what we're dealing with. So we have the three components. We have protons, neutrons, and electrons. Okay. The protons and the neutrons are the only of the three, the two of the three that are inside the nucleus. And the nucleus is extremely small and extremely dense in comparison to the rest of the atom. So to give you an idea of how small the nucleus is, here's a good comparison. So imagine Yankee Stadium, right? Or whatever. It's football season, so Giant Stadium or whatever. Well, MetLife Stadium. So you take a penny in MetLife Stadium, a penny, fine, it could be a quarter, whatever, a coin, and you put it in the middle where they do the coin toss in the beginning of the game. You put it in the middle, right? The size of that coin in relationship to the entire stadium is the size of the nucleus. So the nucleus is less than 1%, much less than 1% of the size of the atom. But the nucleus basically dictates most of the chemical properties of that atom because it holds the neutrons and it holds the protons. And it's extremely small and extremely dense. So what does that mean? That means the rest of the atom, that's not including the nucleus, is mostly empty space. So that's weird to think about, that everything in our existence, which is all composed of atoms, is mostly empty space, a vast majority. 99% of everything that we know is empty space. That's insane. But these atoms are so small and they are so close together, our mind doesn't process the difference between empty space and these atoms that are so close together. So we just assimilate it all as one object. In reality, 99% of things are empty space. So that's really weird to think about. But anyway, so let's look at more in detail. Now, inside the nucleus, you have the protons and the neutrons. So the protons we'll go over first. They are positively charged. So from the prefix pro, so positive pro, fine. That's easy to think about. Positively charged 1. So in the atom, there's no subatomic particle that is more than 1 charge. So that's either +1 or -1 or 0. So they're located in the nucleus, like I said, and they have a mass of 1 atomic mass unit. So we'll learn about the mass soon, but it's very important to know for all these three, for when it comes time for the quizzes and or not quizzes, but for the homeworks and for the tests, to know the location, the charge, and the mass of each of the subatomic particles. So I'll say it one more time. Proton, positively 1 charged, located in the nucleus with the neutrons, and has a mass of 1. So right now, that's the only thing that has mass. Now let's look at the neutron. The neutron is neutrally charged, hence by the prefix neut. So neutral, yeah, so it makes sense. Then it's also located in the nucleus with the proton and also has a mass of 1. So generally, the only difference, if we're talking vaguely, the only difference between a proton and a neutron is the proton has a positive charge of 1. Technically, the masses are a teeny bit different, but for our case and purpose, we're not going to focus on that. So does that make sense about the proton and the neutron? No? Okay, cool. So now the third one, which you've probably heard of, is the electron. So the electron is negatively charged -1. And they are not in the nucleus. They are located around the nucleus. They orbit the nucleus really fast, kind of like how planets orbit the sun. So they're located in different, what we call energy levels. That's each one of these rings we'll learn about this in a later chapter, but each one of these rings around the nucleus represents an energy level. And based on the energy of the electron, the electron can actually skip energy levels, jump back and forth, and really there's a lot of properties that you can elucidate when it comes to electrons and energy levels. But that's basically where they're located, and they move very fast. In terms of mass, this is also important. Their mass is very small. I'm not going to put it 0. It is negligible. So the mass of an electron, if we're talking about this mass unit, so here's what I'm going to do. There we go. So the mass of an electron, if we're talking about a proton being one of these mass units and a neutron being one, an electron is 1 over, I think it's 1,855. That's about right. I think that's it. Yeah. That seems wrong. I don't know why that seems wrong, but it's about that. So what does this mean? This means that you need 1,855 electrons to equal the mass of one neutron or proton, based on this mass unit. So in our problems, the questions that we're going to answer with this information, we can basically consider it negligible. We can make it basically equal 0, because you would need, so the way it works is, so the periodic table has 118 elements, and that 118 number represents the protons. So the biggest element has 118 protons, or no, 118 protons. So you can assume, let's say it's neutral, that means you have 118 electrons, and that is the biggest element. If you put 118 here, that's still less than 0.1 of one of these mass units. So at the biggest possible element, you're still going to have a negligible value when it comes to the mass of the electron, when it comes to getting factored into the molar mass, which we'll talk about in a second. So basically it's 0. Okay, so this is important. I'm going to stop here. Is there any questions on protons, neutrons, electrons, their locations, the charges, the sizes, the masses? Anything at all? Okay, moving on. Okay, so another thing that we will be, okay, I will repeat the situation with the 1855. So electrons are very small, and the mass is very small as well. So the mass of an electron is 1 divided by 1855. That's a very small number. That's very close to 0, 0.000 whatever. That is the mass of one electron, where the proton is a mass unit of 1 and a neutron is 1. So it would take 1,800 electrons to get to the same mass as a neutron or a proton. Therefore, we can say that the electron for our calculations is considered to be 0. That makes sense? Okay, moving on. All right, so isotopes. Now, we will be covering isotopes again, but it's just to hear these, it's good to hear these definitions multiple times. So an isotope is an atom that is the same element as another atom, but they have different masses. And the reason why they have different masses is because they have a different number of neutrons. And this happens. Why does it happen? Because there are some, or actually most elements have more than one, we call it happy or stable states in terms of its proton and neutron number. So the idea of elements and the subatomic particles in general is these atoms and elements want to be happy. They want to be happy. And happy means stable. So when something is stable, that means the energy that is created or that is exerted inside it is not overtaking the energy that is keeping it together. So it's not going to explode. It's not going to be volatile. It's going to be stable. So if you have unstable isotopes, it's called radioactive isotopes. But we're going to talk about stable isotopes right now. So there are many different isotopes of and really different elements. Some elements are what we call monoisotopic, meaning they only have one isotope, and fluorine is an example of that. So it only occurs in one isotope. There are several other ones, but most elements have maybe 2, 3, or even 4 isotopes that they're comfortable with. And what it means is, so if we went back to what we just learned and talk about masses, so the mass of I'll put M proton equals 1, M neutron equals 1, and M electron equals 0. So this is saying that all of the mass inside the atom is the sum of the protons and the neutrons, which is about accurate. For this class, it's about accurate. Some of my professors would disagree, and it gets more technical than that, a lot more technical. But let's just say the mass of the proton's 1 and the mass of the neutron is 1 and the electron 0. So what we can say is that all of the mass of the atom is inside the nucleus. So let's take that back. Let's take that idea back. So I'll say it one more time. All of the mass of the atom is inside the nucleus because the nucleus has both protons and neutrons. Now, let's take it back to that MetLife Stadium example. Imagine that coin in the middle of MetLife Stadium had all of the mass of the stadium. All of it. So there's thousands of tons of steel in concrete. So all of the mass of MetLife Stadium fit into that coin, which we can't even fathom that amount of denseness. That is the scale of the atom, of the nucleus's weight, nucleus's mass, compared to the rest of the atom's mass, which is virtually empty space. You have the electrons buzzing around, but that's about it. Yeah, so that's crazy. So then an isotope is when we have a different number of neutrons. So let's just know that for now. So the neutrons change. There's several stable states that can have different number of neutrons and elements, and these are called isotopes. Okay, so any questions so far? No? Okay. So this is another very important concept. Now, these elements, these atoms, are extremely small. So we're going to have to use big numbers to deal with them. There is no way we can do real-world calculations and experiments when it comes to one atom to one atom, or even thousands or hundreds of thousands or millions of atoms. Those numbers are just not big enough. So they had to make a new number. And this number was called Avogadro's number. So Avogadro is a scientist, and a lot of people, you could say it's Avocado's number. That's funny, but so Avogadro's number is a number that was calculated which was created as a standard for the quantity known as the mole. So here's the mole. So a mole is the number of atoms in 12.011 grams of carbon-12. So carbon is the standard, the universal standard, because we're carbon-based organisms. They just made it the universal standard for this mass or this number system, this number, that definition, number equality, if you will. So what this is saying is that, and we'll talk about why this number is important, but this Avogadro's number, so 1 mole, so it's not like the animal, it's just like the quantity. So 1 mole equals Avogadro's number of particles. That's the best way to write it. And then Avogadro's number of particles, that means it's 6.022 times 10 to the 23rd. And it doesn't have to be atoms. It could be really of anything. Particles. Okay. So, why do we use this number? We use this number because it's a model. So it helps us, these atoms and molecules are so small that it helps us scale them up to tangible substances. Normally the mass of an atom is 10 to the negative 30, 10 to the negative 31 or 32 or 33. Really, most of the time 10 to the negative 33 kilograms. We can't even fathom that 10 to the negative 33 number. That means point and then 31 zeros, at least 30 zeros, and a number. We can't even fathom how small that is. So, and we can't measure that. And I don't care what scale you use, you can't measure that. So we need to have a better model to represent these atoms and molecules in a larger scale so that we can do experimental techniques and make chemical reactions, visually observe chemical reactions with them. So that's why we came up with Avogadro's number. So now, to give you an idea of how big this number is, this is important. So the 6.02 times 10 to the 23rd. This means it's basically a 6 with 23 zeros after it. So you'd be like, oh yeah, it's really big. To give you an idea of how big that is, I'll give you some comparison questions, and you can say the answer in the chat. Now, do you think there is a mole? So this number, this Avogadro's number of trees on the Earth. Think about trees on the Earth. So you have the Amazon, you have all these different rainforests, you have New Jersey, you have every country really has trees. Russia has a lot of trees. They have evergreens like all over, millions of square miles. So all those trees added up. Do you think it's Avogadro's number, this huge 6.02 10 to the 23rd? Either yes or no. No. Okay, good. Good job, Devin. So the answer is no, right? So do you think there's more than a mole or less than a mole of trees? Good, less. Awesome. So there is a lot less. It's a huge amount less of trees than there is particles in Avogadro's number. Now, what about blades of grass? Blades of grass. Do you think there's more or less? And Kaylee, I will get to that. So, do you think there's more or less blades of grass on the entire planet than there is particles in a mole? Okay, good guess. Around the same. And thank you for participating. More. Okay, good. Thanks for participating. The answer is actually less. So blades of grass. Think about that. Think about how many blades of grass there are on the planet. We can't think about it, but try. That number, that blades of grass number, is significantly less than the number of particles in Avogadro's number. So, all right, blades of grass is not enough. Now, do you think what about Avogadro's number of grains of sand? Think about that. That's all the beaches, all the oceans, and all the deserts. Deserts, there's so many deserts, and the sand goes like miles deep in the desert. So think about that. Or you can write the answer in the chat. So do you think there is more than a mole or less than a mole of blades of grass? Not blades of grass, sorry, grains of sand. Okay, so yes, Devin got the point that there's less, but a lot of you think there's more. And that makes sense. That totally makes sense. If I was learning this for the first time, I would think there's more because like blades of grass or grains of sand, there's so many. There's like you can't even count. How do they even count that? They probably did it by like surface area approximations, but that's an insane number. Now, we do know we can approximate how many grains of sand are on Earth. We can. So let's do that right now. Now there are, your homework is to go around to the beach and count them. No, I'm kidding. Okay, so approximately there is 3 times 10 to the 18th grains of sand. That is a huge number, right? So let's compare that to Avogadro's number, 6.022 times 10 to the 23rd is going to be per mole. This means let's just let's say this is negligible, the 3 and the 6. Let's just look at the exponents. This means that the difference between grains of sand and number of particles in a mole is 10 to the 5th. So 10 to the 5th is the difference between 10 to the 23rd and 10 to the 18th. Not the difference meaning subtracted, I mean divided by. So that's like the multiplicity difference. So what that means is that if you take the grains of sand on the Earth and you multiply them by 10 to the 5th, really it's 2 times 10 to the 5th, so double that, you get a mole. What is 2 times 10 to the 5th? 2 times 10 to the 5th is 200,000. Think about that for a second. There is not 200,000 more, 200,000 times more. So there is 200,000 times more particles in a mole than there are grains of sand on the Earth. That means if you were to think and like, all right, let's get a mole of sand, of grains of sand. A mole of grains of sand will encompass the Earth thousands of miles deep. So think about the amount of sand we have now. Multiply that sand by 200,000. That would be greater than the mass of the Earth. That would encapsulate the Earth. I can't even imagine how many miles, thousands of miles deep in sand. So does that give you an appreciation for how big this number is? And is there any questions on how big this number is? And there's a point to this, I promise. Okay. All right. So this number, the reason why it exists in the first place, because we're like, okay, what the hell? Why do we even need it? Because it can't quantify anything on the planet. Why do we use it? All right. So the atoms. Let's do a different element. Let's do oxygen. In 16 grams of oxygen, well, let's do this. 32. So 32 grams of oxygen gas. So that's O2. That's the air that we breathe. 32 grams of the air that we breathe. That might take, I don't know, 3 or 4 minutes of breathing to get that much oxygen gas in you. That amount of gas, and that's not a lot. You could fit that in a capsule. It weighs nothing, and whatever. That amount of gas, 32 grams, has an Avogadro's number of particles of O2 in it. And it can fit in your hand. It can fit in a bottle. It can fit, it's very small. It's tangible to us. It's on our level of tangibility. Gas you can't really quantify, but let's just say water. 18 grams of water, which is equal to 18 milliliters of water. So 18 milliliters of water, which is nothing, that's a sip. 18 milliliters of water has an Avogadro's number of water molecules. And that number is so big that we can't even imagine the grains of sand on the Earth as a mole. It's not even close. It's 200,000 times off. But 18 milliliters, which is just a sip of water, contains that many molecules. That is just to give you the scale difference of how big a mole is, and more importantly, how small the atom is. That we need such a big number to represent it in a tangible substance that we can do reactions with. So I hope it blew your mind. But is there any questions on it? And we'll see how this number comes into play in calculations. It will be important. No? Okay. All right. So with this number and with the knowledge of knowing what the mole is, we can come up with the molar mass. The molar mass is, all that means is the calculated mass in 1 mole of either an element or a compound. So the way you figure it out is that molar mass is the sum of the atomic masses of all of the elements in a compound or a molecule. And these atomic masses, you can get them from the periodic table. And the example I just used in the previous slide, I said that the molar mass, well, I didn't say this out loud. I didn't say this in this terminology. I didn't use the word molar mass yet. But I said that 18 grams of water has 1 mole of particles of water. That means the molar mass, or the mass in 1 mole of water, is 18 grams. And the way you figure out that 18 grams is you break it down into the masses of hydrogen and the masses of oxygen that are listed on the periodic table. So hydrogen has a mass of 1.01. Oxygen has a mass of 16. So hydrogen is about 1. So 1 times 2, because there's 2 hydrogens, is 2, plus 16 is 18. And that's where you get this 18 grams per mole from. That's what G per mol is, grams per mole. So please ask questions about this, because that's very important. We're going to do examples, but that's important. Or if you don't have any questions, that's fine too. No? Okay. All right, so here is the periodic table. This is not a very good picture of it because you cannot see the masses, but I will get a periodic table. Okay, so here we go. All right, so you should also, maybe you should see it, or maybe you don't. Hold on. Yep, you should see it. Okay, so here's the periodic table. And you see that there's 2 numbers on every symbol. So let's look at, I don't know, beryllium. Beryllium is up here, element number 4. So the top number, and can someone please unmute your microphone? Okay, so beryllium is atomic number 4. So atomic number 4, what this top number means is that's the number of protons. That's what we call the atomic number. And that's the number of protons that are in the element. So beryllium has 4 protons. Fine. The bottom number, these decimals, that is the molar mass. So that's what we're going to be focusing on today. That's the molar mass. So beryllium has a molar mass of 9.012 grams. This means that on average, or it's called the average atomic mass. And we'll learn more in detail what that is, but it's just the atomic mass. So if you take a mole of particles, so Avogadro's number of particles of beryllium, it will weigh 9.012 grams. So that's what this molar mass means. So with this information, I'm going to keep this periodic table up here, and then we'll put this back up. So with this information, we can figure out, let's do examples. We can figure out the molar mass of anything. Seriously. Just knowing that, we can figure out the molar mass of anything. So let's do an example. Let's do through 3 examples. So we'll do Na2O. We'll do NaNO3. Well, no, not Na. Too many sodiums. Where's the eraser? The eraser's not working. All right, whatever. So we'll do FeNO3 2. And we'll just do those 2 examples. This covers all the concepts. Now, the way to figure out molar mass is very simple. You just find each of the atoms or each of the elements on the periodic table, and then you add up the masses. So we have Na2O. So that means we have 2 times the molar mass of Na plus the molar mass of oxygen. So let's look at our periodic table and see what these numbers are. So Na is right here, sodium. So can anyone tell me what's the molar mass of sodium? Good job, Kaylee. So you have 22.99. When it is this close to a whole number, for example, 22.99, hydrogen is 1.008, oxygen is 15.999, you can round up to the whole number. If it's somewhere in the middle, such as boron, which is 10.8, it's not the best to round up because it'll be a little bit off, or especially cases where, like chlorine, you have 35.45. That's kind of in the middle between 35 and 36. So you can leave that as is. Now, that's always a common thing that people have trouble with is, when do I round, when do I not round? If you want to be safe, don't round at all. Just put the numbers in your calculator. They're correct numbers. But for something, I'm just telling you, for something like oxygen where it's 15.999, you can round that up to 16. But for ones that are in the middle, it's not you might lose a unit of measure, a unit. Okay. So sodium is 22.99, and the other element was oxygen. And we know oxygen is 15.99 or 16. And sodium is close enough to 23 that we can say it's 23. So we'll do 2 times 23 plus 16. And what does this equal? So 43 plus 10 is 53, plus 6 is 59. So 59, and the unit is very important, grams per mol, which is mole. Or we can write mol, doesn't matter. So this would be your answer for something like this. Does that make sense? Is there any questions on how I got that?
Can you repeat that again?
Yes. So for any compound, let's say if it's Na2O, the way we find the molar mass is we add up the molar masses from the periodic table of each individual element. And then we multiply that by the number of that element in the formula. In this case, there's 2 sodiums and 1 oxygen. So it would be 2 times the mass of sodium, which is 23, plus the mass of oxygen, which is 16, to get our answer.
Okay, got it.
Okay. Anyone else have any questions? We're going to do another example. Okay. So next. So this compound is called, what is it called? Iron 2 nitrate. So it's called iron 2 nitrate. And we'll talk about naming in chapter 4, I think. Iron 2 nitrate. Okay. So iron 2 nitrate, let's figure out the molar mass. So let's go to our periodic table and look at iron. So iron's right here. The molar mass of iron is 55.845. So let's just put 55.8 is fine. Plus. So now it gets a little tricky. We have these parentheses, and we have a 2 out here. So can anyone answer this question? So what do we do with that? There's actually 2 correct answers, but how can you think of that? NO3 parentheses 2. What does that mean?
Do you multiply it?
Exactly. So this means that there's 2 packets, let's say, of NO3. So you can say, let's find the mass of one NO3 and multiply it by 2. That's exactly right. So 2 times, we'll do NO3. So nitrogen, let's go back to our periodic table. And we can see that nitrogen has a mass of 14.007, very close to 14. We could just write 14. And then plus oxygen. So there's O3, there's 3 oxygens. So we have to write 3 times 16, because 16 is the molar mass of oxygen. And then we close that parenthesis off, and we get a number. So can anyone do this math for me? So it's 48 plus 14, that's what? 62 times 2, 124, plus 50, 174, 179.8. Did anyone get that? I just did it in my head. 179.8. Is that wrong? Or right? All right, I'll just calculate it myself. Okay, good. Okay, so so I think you maybe made a calculator mistake. Or maybe, if you make a mistake, yeah, your parentheses, something's wrong with your parentheses, because you need the parentheses with this 14 plus 3 times 16, because that is representative of the NO3. So let me just double check. 2 times. Yep, okay. Great. So we got that. Now, is there any questions on really solving for the molar mass? And 16 is from the oxygen. That's the molar mass of oxygen. This O. Okay. So is there any questions on how to solve the molar mass? This is as complicated as it would get.
I'm okay.
Okay.
Thank you.
All right. So good. So now you can do more with these numbers. So you could do more with these molar mass numbers. Once you have the molar mass, some questions early on, I might ask just what's the molar mass? And yes, we'll do another example. So we can ask what's the molar mass? But you can do things with these numbers. You can use them in unit conversions. You can use them in calculations, because what this number represents, let's say for this iron example, is the grams of that substance in 1 mole of the substance. So technically, well, not technically, really, this is a unit conversion, an equality. It's saying that for this compound, FeNO3, almost 180 grams is in 1 mole. Or another way you could say a mole is 6.022 times 10 to the 23rd particles. So you can say that there is 179.8 grams of this compound in an Avogadro's number of particles. That's another way you can say it. And this information can be used in unit conversion. So that's where this comes in. So you can, using the molar mass and Avogadro's number, we can convert from really anything to anything. We can convert from the atoms to the moles to the mass. So all we learned right now is we learned Avogadro's number and we learned molar mass. We can use these we could use them as conversion factors. So we're going to do more examples. So we would calculate molar mass, but that's only going to be part of it. So Avogadro's number, what that means is there is 6.022 times 10 to the 23rd particles. By particles, it could mean atoms or molecules, but particles is more accurate because it could be either or. That many particles in 1 mole. The molar mass means that there is, I'll just put molar mass grams, whatever the number is for that compound, that number of grams per 1 mole of substance. So we can use this as a conversion. So let's just go to an example. Let's see. So what is the mass of two moles of NaCl? So table salt, what is the mass of 2 moles of it? Now we can go from the moles, which is 2, to the mass of the element or the sample by using the molar mass. And I have crash chem videos that cover this very well. There's a molar mass one, and there's a what we call mole calculations one. So I definitely suggest going over those. Now, what is the mass of 2 moles? Now, first, let's try to figure out the molar mass of NaCl. And here's a quick tip. If you're ever doing questions and you see a compound and you don't know what to do, calculating the molar mass is a good idea because it may give you more information and something may click. So the molar mass of NaCl, Na is 23. Cl, so let's look at Cl. Cl is 35.45 right up here. Now for Cl, we cannot round it because it's kind of in the middle of each of the numbers. It's in between 35 and 36. So we could just write it as is. 45.45. And then once you add these together, you get 68.45. Oh no, 35. It's supposed to be 58. 58, 35. Yeah. 35.45 and 58.45. All right. So 58.45 is grams of NaCl in 1 mole. So if that's true, what is the question asking? What is the mass of 2 moles of NaCl? Well, we know that 1 mole is 58.45, so we can multiply by 2. 58.45 grams per 1 mole times 2 equals 116.9. 116.9 grams of NaCl in 2 moles. So yeah, same thing. That's correct. Okay. So, is there any questions on that? That was a very simple example of converting from moles to grams when we have our molar mass. So I'm going to do another one that involves Avogadro's number. Is that good? Okay. So let's see. Let's do how many atoms are in 0.70 moles of, I don't know, chromium, whatever. Okay. So this question is asking for how many atoms are in 0.7 moles of chromium. So let's go back to our conversions, and we'll see that the way to convert moles to our atoms is by using Avogadro's number. And Avogadro's number's equality is 6.022 times 10 to the 23rd, let's say atoms in our case for this question, is 1 mole. So if Avogadro's number is 1 mole, how many is 0.7 moles? That's what this question is asking. So to do that, well, first, does that make sense? To understand what this question is asking and what you need? So you need to figure out the atoms that are in 0.7 moles when you know that Avogadro's is 1 mole. Good?
I'm a little confused now.
Okay.
Sorry.
No, don't be sorry. Please do not apologize for asking questions. Like, I want you to ask questions, because if someone has a confusion, I guarantee half the class has the same confusion, but they're afraid to ask questions. So, because I was like that in school too. I'd be scared to ask questions because I was afraid I would be stupid. So there's no such thing as stupid questions, especially when it comes to chemistry, because it's pretty hard. All right.
Okay.
So let's break down the question. So how many atoms are in 0.7 moles of chromium? It doesn't matter. I'll cut to the chase. It doesn't matter what it is. It could be chromium, it could be oxygen or fluorine, whatever. We're converting the 0.7 moles. So 0.7 is less than 1. So that means it's less than 1 mole. And we're seeing how many atoms are in that many moles of your substance. The information that we know is that our 6.022 times 10 to the 23rd atoms, the Avogadro's number, is equal to 1 mole. So how many atoms are in 0.7 moles? If this many is 1, then how many is 0.7? You can set up a proportion. You can do a unit conversion thing. I'll set up a proportion because logically it makes more sense. So we're looking for X atoms over 0.70 moles. Now I set this up as a proportion, and I'll explain it one more time. Avogadro's number of atoms is the number of atoms in 1 mole. And that is equal to, and that ratio is equal to the number of atoms in 0.7 moles. So it's the same ratio. So what we do is we solve for X. And you can solve for X however you want to. Now in this class, math like solving for X, you should know how to do that. If you don't, you need to go look online again. And I can give you some resources for that. But I'm not going to spend time going over how to solve for X. But what I would do here is you do your whatever cross multiplying, whatever you want to call it, 0.70. The 0.7 cancels out, and you're multiplying this by 0.7. So then it would be the 6.022 times 10 to the 23rd times 0.7. Did I say 0.07? I meant 0.70. So multiply that together. Let's see, what's 0.7? 0.7 times 6.022. That's 4.21. So the answer to this is 4.21 times 10 to the 23rd atoms of chromium in 0.70 moles. Okay.
Okay, I got it.
Yes.
Thank you.
Okay, good. Anybody else have any questions on that? It's okay if you do. No? Okay. All right, so we will be covering this concept more and more each class. I'm just giving you a preview, and the best way to learn this stuff, because it is difficult, as you're probably noticing, is repetition, repetition. So if you feel freaked out and if it's too much for you right now, that's okay. We're going to keep learning it, and the worksheet is going to be a little bit more. The worksheet's kind of easy. The homework is going to be a little bit more. Chapter 3, we'll do a little bit more, and we will get the hang of it eventually. Okay, so basically, we're really basically almost done. So this guy, Dmitry Mendeleev, in 1896, he figured out a way to arrange the periodic table, and with what they had at the time. So here was the original periodic table. They didn't have all the elements yet. They only had about less than half of them. But here's what they figured out. Now, a lot of traits of it are still the same as they are today, but so the periodic table is, here's the way I like to describe it, is the best human representation of ordering the elements. It's not perfect, but there are a lot of trends and patterns in the periodic table that are important, or that make it make sense a little bit more, such as the size of the atoms increases as you go down the periodic table. The charges of the atoms in the periodic table are, they have group 1 is all +1, group 2 is all +2, going down the line. So there's a lot of patterns that we're going to learn about in the upcoming classes that have to do with the periodic table organization, and it's very important. Okay, so, and we'll go over one of those. So looking at this periodic table, we'll go over some basic organization right now, just to get your feet wet with it. Now, you can see there's all this color coding. Now, there's different parts of the periodic table, different element types. There are alkali metals, which are in red, alkaline earth metals, which are in orange. There's transition metals in yellow. There's metalloids in this green color. There's post-transition metals, or what they call basic metals here, over there. And then there's halogens, noble gases, and there's non-metals all up here. So, and then there's lanthanides and actinides, which are, they call them actinoids here. They're really actinides. Same thing, different terms. But we're going to learn about all of these different levels of organization. Some basic high-level things are the left side of the periodic table. So this whole side up here, including the yellow, these are where most of the metals are. So the only non-metal that is on the left side of the periodic table is hydrogen. Hydrogen is weird. It's atomic number 1. So that means it has a proton number of 1. It's the smallest element, but they didn't know where else to put it because it has some properties that are similar to these metals in group 1, the group meaning the vertical column. It has some similar qualities, such as when it becomes an ion, meaning when it has charge, it has the same +1 charge as the other ones in the series. But the other ones in the series are metals, whereas hydrogen is a non-metal. So it kind of belongs over here, but they had nowhere else to put it. So there is actually, you can't completely understand the periodic table because it doesn't 100% make sense. Sometimes it's just they didn't know where else to put it. Like, honestly, though. So a lot of questions. If you're seeing the periodic table and you're just looking at it right now, you might think, why are these groups down here, the lanthanides and actinides, why are they down on the bottom? And the real answer is because they didn't know where else to put them. If they put them right here, where they actually belong here, it would be the periodic table would be too long and it wouldn't fit on the page. Honestly, that is why they do that. So you can draw the periodic table on a normal 11 by 8, whatever, 8.5 by 11 piece of paper without making it too squished. So that's one example of the best representation that humans can come up with, the most sensible one. Because if you think about it, we don't create science. Humans did not create science. we are observing well, we created scientific techniques to for our mind to wrap around these concepts the best they could. But we didn't create atoms, we didn't create molecules. We discovered that all of these things existed. And we're organisms too, just like chimpanzees and cats. We're mammals and we're organisms. So this is an example of our best effort to understand the natural world around us and to create order from it, is the periodic table. And that's what every equation is. That's what every law is, law of definite proportions. This is what really every mainstream scientific fact is our best way of interpreting what happens based on the instrumentation, the measurements, and the concept. Because there's limit to human understanding that we cannot conceptualize. And that goes into physics and the fourth dimension, the fifth dimension, all that stuff. We can't conceptualize that at all. But there are ways to make metaphors to kind of understand what happens based on the equations that we derive to note its existence. But that can go into a whole different conversation. So there's a periodic table, basic terms. You have the metals all on the left side over here. The non-metals are all on the right side here. So the non-metals, so even though it says non-metals are in this light blue, the halogens, all of these halogens in the dark blue, and the noble gases in purple are also non-metals. They're just a different class of non-metals called noble gases and halogens, but they are all non-metals as well. Then you have metalloids, which are here, which they kind of have traits of both metals and non-metals. And then these light green ones, honestly, they are the same thing as transition metals, almost all of them, but they didn't know where else to put them. So they have to put them here. And they had the proton numbers they worked out the same, where it's like the zinc is 30, gallium is 31. They couldn't put gallium somewhere else because it needs to be in number order. So the main order of this periodic table, as you can see, the top number of the symbol goes in number order. So hydrogen is 1, helium is 2, and you read it like a book. Nitrogen or lithium is 3, beryllium, boron, carbon, nitrogen. And there's a whole song for the periodic table. But regardless, this is the number of protons. So let's get back to the slideshow. Now, here's the chemical symbol. So here's iron. You have the atomic number, which is also known as Z, but just the atomic number. The atomic number is the same number of protons. So very important concept. Atomic number. Number, protons. Very, 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 very important. So I cannot stress that enough. That the atomic number is the number of protons. So oxygen has an atomic number of 8. Therefore, it has 8 protons. There is no such thing as 2 of the same element with a different number of protons. The protons are the characteristic thing of that element. You cannot find iron without 26 protons. If it has 25 protons, it's not iron. If it has 27, it's not iron. If it has 26, it is iron. That's the proton. So the protons always stay constant. It's a very important thing. So protons, or I'll put proton number, always constant. Okay. So we'll learn in the other classes, like we touched on isotopes where the neutrons can change, or you could either add or subtract them. The electrons could also change. You could have more electrons, less electrons, and that creates a charge. And we'll learn about charge and ions in a different class. But so that's the atomic number. That's the first one. Then you have the chemical symbol, which I don't know, it's just the symbol for the element. Iron is Fe because it comes from ferrate and ferrium. That's the Latin derivation. So we just call it Fe, but we call it, since we're English, we call it iron. And then the atomic mass. So it's what we call the average atomic mass, is the bottom number, which is usually which is definitely the atomic mass you're going to use for calculating molar mass. So this is telling you the average atomic mass. If you take 55.847 grams of iron, it is almost exactly 1 mole. So it's telling you the molar mass of iron is that bottom number, and really of any of the elements. Okay, so I know that the lecture is almost over. So is there anything outstanding? Any questions that I didn't answer? Because I know it's a lot. We're kind of like cherry picking information, but this lecture is jam-packed with a lot of important information. So I do recommend, because it is a shorter one, probably around an hour, that you do go back and watch the YouTube video after I post it, because just hearing it again and again will help you. And then also going on Crash Chem and looking up, I have videos for really, I think half the videos are for chapter 2, because that's how important it is. And then a question, so can you give an example of the law of conservation of mass? Sure. So if you add, I don't know, if you have, let's do a reaction. So if you have 20 grams, or whatever, I wrote 2, I said 20, but I said 2 grams. 2 grams of sodium, you're adding it to 2 grams of chlorine to get sodium chloride. You're going to get NaCl, and it'll be 4 grams. This is not technically correct, but just for the conceptual idea of the law, it is true, because mass is not being created or destroyed. You're not going to, in a perfect system, you're not going to get 3 grams or 5 grams. It'll be exactly the same as the starting materials, assuming they all react completely. So does that make sense? It's just matter cannot be created or destroyed. Okay, so again, don't apologize for questions. So the grams is just the mass. If you have 2 grams of sodium and you add 2 grams of chlorine, let's just say theoretically you get 4 grams of sodium chloride. That's both of them added together. It's saying that the mass cannot be created. You can't have more mass come out of thin air, basically, and you can't have mass randomly lost into thin air. So everything in the universe, this goes into universal laws, that the mass of the universe is constant. You can't add mass to the universe out of nowhere spontaneously, and you can't remove it. Things blow up and you can transform mass into energy, but you can't lose stuff permanently. So, okay. Okay, so is there any questions about the calculations, about the periodic table, maybe about the organization or atomic mass? Molar mass was a very important concept we learned today. The rest of it's like green chemistry. Green chemistry is important. Here are some videos. So, important things for studying. Obviously, I have Crash Chem, but I have, these are not my videos, but they're just really good videos, like maybe Khan Academy or just other good online YouTube resources for understanding the components of an atom, the mole, the molar mass, etc. So definitely take a look at those when you're studying, and they're a lot shorter than this lecture. So they're probably 5 to 10 minutes each. So that's a good way to study. Well, before we start the worksheet, let's do one more example of molar mass. So we'll do, I don't know. Let's go to the periodic table. I'll make something up. Let's do tin oxide. Sure. So tin is SN. And we'll make it. So this compound is actually called tin 4 oxide. And we'll talk about the 4. This is Roman numeral for 4. We'll talk about that in another class. But I want to show you some of the names, so then you start thinking about it. So tin oxide, tin 4 oxide. The molar mass of this would be the molar mass of tin plus 2 times the molar mass of oxygen. So we know the molar mass of oxygen. We're really good at that. We've seen that twice already. It's going to be 2 times 16. The 16 is the molar mass of oxygen. There are 2 of them, so you get 2 times 16. And we can go back to the periodic table to figure out for tin. And you see that, can someone tell me what's the molar mass of tin? Sn. It's around here. I'll just vaguely wiggle my mouse.
78.97? 78.97?
No.
Wait, where's 10?
It's 11871.
Good. So tin's right here,
okay.
Sn. Yeah, it's got a weird symbol.
SE, sorry.
Yeah. Se is selenium. Yeah. So the symbols are something that you have to get used to, but so a good question you might be thinking of is, what do you do on the exam? The exams will have periodic tables with them. You don't need to memorize any of this. Don't worry about that. But the symbols are kind of weird. Like you have, where's tungsten? Yeah, W is tungsten. How the hell does that make sense? Nobody knows. It's actually just derivations, but from different languages. But they're weird. Like Au is gold, aruum, and the argentum, Ag, is silver. So that's from like Latin, and that's from Latin. But a lot of them are weird symbols. Sb is antimony. That's weird. So again, it's a human construction for order. So okay, so tin, it's 118.71. Let's just say it's 118.7 because you can't round to 119 because it's just 0.7 is just too close to do that with. It's too much in the middle. Let's see. So we add those up. We get 118.7 plus 32. This would be 150.7 grams per mol. So that would be the molar mass of tin 4 oxide. Okay, so I'm going to end the recording.